So this is lecture 4 on infinite dimensional Teichmüller spaces, and we're going to focus on bi-holomorphic and bi-Lipschitz maps between Teichmüller spaces. Okay, and before we do that though, there's just one comment I want to say about the extremal maps and geodesics thing that we were talking about yesterday. One point I should probably say is that one of the observations that leads to some of the results I was talking about and some of the results I didn't talk about is that a mapping is extremal when it's Teichmüller. Complex dilatation is extremal when it's Teichmüller class, if and only if it's extremal in its tangent class. So, if you remember, this is the class of complex dilatations which represent the same tangent vector at the base point. And this is a nice linear class. This is not a nice linear class. So you can find extremal mappings by doing things with this class. And the same holds for the uniqueness. So you're uniquely extremal up here in this class if and only if you're uniquely extremal in that class. The first thing I'll mention in this section is the asymptotic Teichmüller space, which is a variation on Teichmüller spaces. And well, we'll define it and we'll talk about some results on that a little bit later in the talk. Firstly, a quasi-conformal map from the upper half plane to itself is called asymptotically conformal if and only if the complex dilatation, well actually no, let's read it this way, if and only if for all epsilon greater than 0 there is a compact set K in the upper half plane, so that if you look at the complex dilatation of F and you restrict it to values outside this compact set, then that is less than epsilon. So remember that the complex dilatation, if it's 0, that corresponds to being conformal. So if you're very close to 0, then you're very nearly conformal. So this is saying as you get closer and closer towards the boundary of the upper half plane, you're becoming more and more conformal. So in particular, a conformal map is asymptotically conformal. So we can put an equivalence relation on quasi-conformal maps in the upper half plane and G-invariant quasi-conformal maps in the upper half plane to get a similar definition for asymptotic Teichmüller space based on the definition for Teichmüller space. So let S be a surface of infinite type. Then the asymptotic Teichmüller space of S is this set of, well, how should we write this? So it's the Teichmüller space quotiented by the asymptotic Teichmüller relation, where two elements are equivalent two elements of Teichmüller space are equivalent under the asymptotic Teichmüller equivalence relation, if and only if, when you look at the class of F composed with G inverse, that contains an asymptotically conformal representative. So in other words, if you start with your space S and you have quasi-conformal maps F and G applied to S, then if we do G inverse composed with F, well, that's going this way. What we're saying is that these two mappings are equivalent under this asymptotic Teichmüller relation if and only if F composed with G inverse is homotopic to some asymptotically conformal map. So in the Teichmüller space definition, we don't have this conformal. So we don't have this asymptotically. We have this is homotopic to a conformal map. Here we have asymptotic conformality. So if we look at surfaces of finite type, then asymptotic Teichmüller space just reduces to one point. So this is a set that's only interesting when you're looking at surfaces of infinite type.
Don't you have to define, because according to your definition of this, don't you have to define asymptotic conformal in general for a surface?
Well, yeah, I'm trying to produce something.
Yeah,
Sure. Well, I mean, you lift to the upper half plane,
yeah,
and then you restrict to some fundamental region.
okay. But that's different than that statement, than that definition. Because contact sets could always be moved to the boundary.
Yes,
Under the group.
This is true.
Yeah, fundamental region.
Yeah. Let's make a note of that. Thanks. So asymptotic. Conformality of a surface corresponds to asymptotic conformality restricted to a fundamental domain in the upper half plane. So putting up the diagram that we had yesterday, where we started off with Beltrami differentials, and we can project down to Teichmüller space, and we then have the Beers embedding. Of this down into Q. Well, we now have another projection from Teichmüller space over here to asymptotic Teichmüller space. And there's a corresponding embedding to the Beers embedding for asymptotic Teichmüller space. Beers embedding reduces a map, or we call it the Beers embedding, I think, capital phi. So the Beers embedding induces a map phi hat from asymptotic Teichmüller space to Q of L comma G quotiented by Q0 of L comma G. So I guess I have to define what Q0 is. So this is the space of quadratic differentials in Q which vanish at the boundary. So Q0 of LG that's the set of these phi, so that for all epsilon greater than 0, there exists a compact set K contained in omega, a fundamental region for G in L. So that, well, we had an expression for the Beers norm, which was the hyperbolic supremum norm. Well, we want that expression, so rho to the minus 2, the hyperbolic density on L to the minus 2, and phi, and we want to restrict to omega less k. We want the supremum norm of that to be less than epsilon. So this expression is going to 0 as we go towards the boundary of our fundamental region. So I think I mentioned it back in the second talk, but if S is of finite type, Q0 equals Q. Then phi hat is a local homeomorphism. This is a result of Gardner and Lukic. And subsequently, it was shown that phi hat behaves like the Beers embedding in that it's a biholomorphic map. Onto a bounded open subset of Q quotiented by Q0. So for infinite type surfaces, you may be able to say things about asymptotic Teichmüller space, which may be of use. Now, in the rest of the talk, we're going to talk about biholomorphic maps and bi-Lipschitz maps between Teichmüller spaces. So the first observation is that the mapping class group of S acts on the Teichmüller space of S by F gets mapped to F composed with G, and such elements of MCS induce, well, not just an automorphism, a biholomorphic automorphism of Teichmüller space. So you start with a mapping class in S, that's from S to itself, and then that induces a map on Teichmüller space just given by composition. And it turns out that this biholomorphic map on Teichmüller space, the question is, are these the only biholomorphic mappings, biholomorphic automorphisms of Teichmüller space that you get?
Sorry, Alastair. Can you comment a little bit on the definition you're taking for MCS?
What definition would you like?
I don't know, which one you have in your head?
I think about homomorphisms from the surface to the self and isotopic classes of those.
Okay.
QC. You want QC?
You want?
Yes, QC.
So it's QC homoms.
Yeah.
Okay.
So are these the only biholomorphic automorphisms of Teichmüller space? And let's call these things something. We'll call such automorphisms geometric. So they were induced by an element of the map of the ice group. So the first result in this direction is famous paper of Riemann, where he showed that, yes, for closed surfaces, all the automorphisms of Teichmüller space that you get are geometric. Well, almost all. So if S is a non-exceptional closed surface, and non-exceptional means that, let me make sure I get this right, I think we want the genus, if the genus is G and the number of punctures on your surface, well, we're kind of not having n to be anything except 0 here, but we call it non-exceptional if it's a finite type and 2G plus n is greater than or equal to 5. If this condition doesn't hold, and there's just a few cases where it doesn't, then you get biholomorphic automorphisms of Teichmüller space which aren't geometric, so they aren't coming from an element of the mapping class group. But there's only a couple of cases where that happens. In most cases, all elements of the automorphism group T of S are geometric. Okay, so let me give some of the ingredients of how Riemann proved this, and then how some of the difficulties extending those ingredients to infinite type surfaces were overcome by various people. So the main ideas, excuse me, first thing is to show that the Kobayashi and Teichmüller metrics agree on T of S. So remember here that we're just assuming S is a closed surface, so this is just finite type S. And the Kobayashi metric, the largest pseudometric that you could put on a Banach manifold so that holomorphic maps are distance decreasing. I won't say any more than that. But for example, the Kobayashi metric on a hyperbolic surface agrees with the hyperbolic metric.
Mm-hmm.
So this implies that if you have a biholomorphic automorphism of Teichmüller space, that induces complex linear isometries spaces at, say, tau and f of tau respectively. So if you start with a biholomorphic automorphism, then you get the fact that it preserves the Kobayashi metric, which means it preserves the Teichmüller metric, which gives you, when you work it a little bit, complex linear isometries in the cotangent spaces between tau and f of tau. So the tangent space, we said, can be identified with these various spaces of quadratic differentials. And the cotangent spaces can be identified with the various Bergman spaces. But for finite type, the cotangent space and the tangent space can be identified, they're the same thing. So these cotangent spaces can be identified with Bergman spaces. And an isometry between these Bergman spaces gives you that the corresponding Riemann surfaces are conformally equivalent. So, if you remember, yesterday I said that at each point in Teichmüller space, the tangent space corresponds to one of these, but as you move around in Teichmüller space, the tangent space you get, it'll be one of these, but the G will change depending on where you are in Teichmüller space. So you'll have Bergman spaces of two different Riemann surfaces which will correspond to the cotangent spaces. And one of the steps in writing this argument is that if you have an isometry, a C-linear isometry between these Bergman spaces, then the Riemann surfaces you're thinking about turn out to be conformally equivalent.
Can I ask you, did you say what a Bergman space is? I've forgotten.
Yesterday, it's
You just say the word.
It's A1, so it's the holomorphic quadratic differentials that are L1 integrable. And 3, once you have this property, use that to conclude F is geometric. And to do this in the finite type case, Royden used the fact that MCS acts properly discontinuously on Teichmüller space in the finite type case. Okay, so this argument doesn't quite go through for infinite type surfaces, so where are the issues? Okay, the first thing is that equality of Kobayashi and Teichmüller metrics on T of S, you need some new ideas when you go to infinite type surfaces. So, the equality of Kobayashi and Teichmüller metrics T of S for infinite type surfaces. Was proved by Kra and Krushkal. And they used Slodkovsky's work on equivariance extensions of holomorphic motions. I guess I'll just say the words if you're interested and look these ideas up. Okay, so this step one, by the work of Kra and Krushkal, that's okay, we can do it. We get that Kobayashi and Teichmüller metrics always agree on Teichmüller space. Okay, the next issue is that here you could pass from the tangent space to the cotangent space straight away because they're the same for infinite type surfaces. The L1 integrable quadratic differentials and the quadratic differentials with that there's hyperbolic supremum norm, they don't agree. So what you need to do is that, okay, you get some, you have some holomorphic map which gives you, by the equality of the Kobayashi and Teichmüller spaces, you get an isometry between the tangent spaces, but then you want to pass to the cotangent space. And Earl and Gardner did that. So Earl and Gardner proved an isometry between all the isometries, by the way, are complex linear. So all the complex linear isometries between Q of S and Q of S1, that gives an isometry between the corresponding Bergen spaces. Okay, and it turns out that it's easier to deal with complex linear isometries on the Bergen spaces than on the Q spaces, so that's why we're doing this stuff. Earl and Gardner also took case of the problem that the mapping class group of S doesn't need to act properly discontinuously on Teichmüller space when you have infinite type surfaces. So they also dealt with the issue that the mapping class group of S need not act properly discontinuously on Teichmüller space for infinite time. So this part 3 here, Earl and Gardner sorted. So what we're left with is this part here, part 2. So if you have a complex linear isometry between these Bergman spaces, do you get a conformal mapping between the corresponding Riemann surfaces? And that was the last part of the puzzle to be dealt with. So, passing from isometries between Bergman spaces to conformal maps between the underlying surfaces was the last piece of the puzzle. And this was dealt with by Lakich for finite genus surfaces. So you can find an embedding of your surface into a finite genus surface, but you might have pulled out, must have pulled out infinitely many punctures to get that finite genus surface. And Markovits did this for all non-exceptional type Riemann surfaces. So as long as your Riemann surface is non-exceptional, which means it's not one of those small group of surfaces, small list of surfaces you started with, so as long as 2g plus m is greater than or equal to 5, then Royden's theorem is true. Every biholomorphic automorphism of Teichmüller space is induced by a quasi-conformal mapping underlying the surface. So the conclusions, if S is any Riemann surface and not of exceptional type, then the automorphisms of biholomorphic automorphisms of Teichmüller space can be identified with the mapping class group of your surface, and if S and S1 are non-exceptional, any biholomorphic, if S and S1 are non-exceptional, and F from the Teichmüller space of S to the Teichmüller space of S1 is biholomorphic, then S and S1 are quasi-conformally related. So there's a quasi-conformal map between S and S1. The point here is that you're not even starting by saying S and S1 are homeomorphic. All you're saying is that you've got a biholomorphic map between the respective Teichmüller spaces, then that gives you the corresponding underlying surfaces must be quasi-conformally related. So we're not assuming S and S1 are homeomorphic, but that drops out as a conclusion. Okay, so what this is saying is that if you have, or at least the steps that Nicola Lakich and Vlad Markovits did, is that if you have an isometry between your Bergman spaces, that tells you something very strong about the surfaces. They're quasi-conformally related. So what about if you weaken the hypothesis that you have an isometry between the Bergman spaces? What if you just have a bi-Lipschitz map between them? Can you then conclude anything about the surfaces? So what if isometries between Bergman spaces are weakened to bi-Lipschitz maps? to this. And finally, I get to say something like that. So if S is a Riemann surface of infinite analytic type, so genus G, n punctures G or n may be infinite, then the following Banach spaces are bi-Lipschitz equivalent, so there's a bi-Lipschitz map between them. Well, Q0 of, let me just write S for shorthand. There's a bi-Lipschitz map between that and C0. There's a bi-Lipschitz map between the Bergman space and the sequence space L1, and there's a bi-Lipschitz map between the Q space and the sequence space little n infinity. So C0 here, its double dual is this, so C0 sits inside n infinity, and those are the sequences that go to 0. And it's good that the Banach dual of this is this, and the Banach dual of this is that, because the Banach dual of this is that, and the Banach dual of this is that. So as a corollary of that, if S and S1 are infinite type surfaces, then there is a bi-Lipschitz map from the Bergman space, for example, of A1 of S to the Bergman space of S1. So again, we're not assuming S and S1 are homeomorphic here. So S could be a Loch Ness monster, S1 could be the plane punctured at the integers, they're not homeomorphic, but the Bergman spaces turn out to be bi-Lipschitz equivalent. So looking at in the bi-Lipschitz class of Bergman spaces doesn't tell you anything about the underlying surface, because you can always find a bi-Lipschitz map between them. So what it also tells you is that we have a bi-Lipschitz map from Q down to L infinity, and we have a bi-Lipschitz map from Q quotient Q0 to L infinity quotient C0. So we in fact have a bi-Lipschitz map on neighborhoods, or locally bi-Lipschitz map, let me put it that way, on Teichmüller space down into L infinity. So the Beer's embedding, remember, it's holomorphic, but it's only locally bi-Lipschitz. So this is locally bi-Lipschitz to here, this is locally bi-Lipschitz to here. Another corollary is that if S and S1 are infinite type surfaces, the Teichmüller space of S and the Teichmüller space of S1 are locally bi-Lipschitz equivalent. Meaning, if you take any point in Teichmüller space of S and any point in Teichmüller space of S1, you can come up with a bi-Lipschitz map between neighborhoods of those points. So I guess a question here, which could go in the open problems session later, is that if there is a global bi-Lipschitz map between, say, T of S and T of S1, does this imply anything about the underlying surfaces? So if you have a biholomorphic map, you know the surfaces are quasi-conformally equivalent. If your mapping is only locally bi-Lipschitz, you know nothing. Is there some sweet spot here where you have a globally bi-Lipschitz map? Does that tell you, for example, that the surfaces are quasi-conformally related? Okay, how long have I got? A couple of minutes. Okay, in a couple of minutes, let me give you an idea of how you might go about proving this, this theorem I just wrote off here in the Q0 case. When you set up a big network of maps that go from between various Banach spaces, so you start off with continuous functions which vanish in the boundary of S, and what you want to do is you want to break up your surface S into lots of little small, relatively compact, let's say they're simply connected regions. And you want to make sure there's countably many of them. So we break this up into lots of little regions that look a little bit like that. Then what we want to do is construct a certain map that goes from here to some space lambda. What is this map that we're going to choose here? Well, it acts on each one of these little pieces of S. And how does it act? Well, you choose some point Wi and Si, and then psi I of f is just point evaluation. And then you make the indicator function on your little surface. So your function, you start with a continuous function, so it's doing whatever it's doing. You break up into little pieces, find some little piece, and then you just smooth it out by making it do this. And this space here, on each of these little SIs, it's constant. So you can obviously map that isometrically well, actually to C0. This is the space of sequences which go to 0 if you start with this. Okay. What you then get for the next ingredient is there's a projection P from from C0 of S to, let me write it as rho to the minus 2 Q of S. So you take Q0 of S. So you take holomorphic quadratic differentials with finite hyperbolic supremum norm, which vanish at the boundary in this sense. So vanishing at the boundary means this expression goes to 0 as you go towards the boundary, so they're contained here. And there is a projection based on Bergman kernels which send you from here to here. Well, you can apply these two maps here. You get something there, and you get X there. The projection you have here corresponds to a projection here, and if you break up your surface into small enough pieces, a normal family argument means that you get a projection here too. So you've got some space lambda living up here, which is isometric to C0, and you have some space X here, and this turns out to be an infinite dimensional complemented subspace of C0. Complemented just means there's a projection onto it. So this is a projection from basically C0 down to here, and then the result of Karczynski says, that may or may not be correct, X is isomorphic, or by Lipschitz equivalent in our language, to C0. So you get a bi-Lipschitz map between here and C0, and then you just pull that back by these two maps, which are relatively nice, and you get that this thing here is isomorphic to C0. And you can do a similar sort of construction for the Bergman spaces and the Q space too. Now let me just finish by throwing another question in there. So the bi-Lipschitz constant you get, the isometric distortion that you get from the Pelchinski result is non-constructive. It doesn't tell you what the isometric distortion is. So is there a universal constant C so that, for example, A1 of S and little l1 are C bi-Lipschitz equivalents for all Riemann surfaces S of infinite type? Or can you come up with a sequence of infinite type surfaces which degenerate in some way so that the isometric distortion that you get gets larger and larger as these surfaces get nastier and nastier? Okay, I think that's everything I wanted to say. Thanks for your attention to the 4 talks. It's been a pleasure to be here in Morelia. It's been a wonderful conference. Thanks to the organisers for their hard work and all the team behind them. So thanks once again.
Any questions for our speaker? Anyone want to thank someone again? Well, let's give another round of applause.